Hello and welcome back to this series of tutorial videos where we are seeing all the different steps that we could follow to define a flexibility workflow in the Scipion Flexibility Hub. In the previous video, we saw how to run the flexibility consensus in order to take different estimations of a conformational landscape, either coming from the same software or coming from different softwares, in order to do an stability analysis and extract only those particles that are more stable. So in principle, we are getting a more reliable dataset. In this video, we're going to see how we can take the particles that we have just taken either from the flexibility consensus or for one of the estimations of the conformational landscapes done with CryoDragon, CERN, HCN, and so on, and apply a dimensionality reduction so we can later on visualize and interactively explore all these conformational landscapes. For that, you can use the protocol that is found in data analysis and called FlexUtils dim red space. If we open the form of this protocol, you can see different options and some parameters that are mandatory. Of course, the first parameter that is mandatory is the input particles, which need to have flexibility information estimated. So they need to come either from the CryoDragon training, the CERN training, HCN training, or the Flex consensus. Once you provide your particles, you can decide the type of dimensionality reduction method you want to use. And here we are providing three methods. First one is UMAP. UMAP is a very popular method nowadays. It tries to provide a more meaningful representation in a reduced space, but trying to keep as much as possible the original shape or the original features present in the high dimensional space. So it's usually one of the best possible choices when you want to analyze conformational landscapes. Problem is that for some cases, UMAP, you need to set up a lot of different parameters, and you can get some artifactual representation. So always my advice when doing this kind of dim red space things is try to run all the different options you have here, like UMAP, PCA, DPLASTIC. And then once you have all of them run, have a look at them and decide if you are getting a nice representation or it looks a bit artifactual, it's easy to analyze, or it's going to be something that is hard to understand. In the case of UMAP, you have different parameters that you can fill, which is the number of neighbors. This number of neighbors will determine whether your reduced landscape is trying to keep the, let's say, general features in the high dimensional space. That means the number of neighbors is big. Or you are trying to keep local features, which means the number of neighbors is small. Usually you put here a number between either 5 or 50 neighbors, depending on how big your dataset is and also depending on the kind of information you want to keep in your reduced landscape. Number of UMAP epochs will determine how many iterations UMAP will do in order to try more accurately your reduced landscape. The more epochs you do, the more accurate you will get your reduced landscape, but also it will take longer. So you need to play with this parameter. Usually 1000 is more than enough to get a good representation. DenseMap is an option that we don't use by default because it decreases performance, but it can be useful in some cases. UMAP is a type of method that has been designed for deep learning. And in deep learning, what we usually want to have is kind of clusters, like different point clouds in our landscape that are representing different classes. Like, for example, if I am training a real network based on images coming from chairs, cars, motorbikes, I want to get a cluster for motorbikes, cluster for chairs, and so on. But in CryoEM, this is not completely true. But because our proteins are not jumping suddenly from one state to another, so we have some kind of continuity between different states. And UMAP is not going to be able to reproduce that in some cases very, very well. So if you put here just in the DenseMap, you are telling UMAP that you want to force continuity into your reduced landscape, which in some cases can be useful. In general, this is not needed, but if you are seeing that your UMAP is getting kind of very dispersed, you can set it to just trying to enforce a little bit more of continuity. Last option, this landscape space dimensions, is not specific for UMAP, it's common to all of these three methods, and it will determine if you want to do a reduction to a 2D space or to a 3D space. Depending on what you choose here, you will be able to use different interactive tools later on, as we will see. PCA is principal component analysis. In this case, PCA doesn't have any kind of parameters, and it's going to do a standard principal component analysis of your high-dimensional space and get either the two first principal components in case of 2D or the three first principal components in case of 3D. PCA is usually not giving very meaningful representations in the sense that it is not able to capture very well very local features in your high-dimensional space because you are only using the very first principal components. Still, if you are seeing that your UMAP is kind of artifactual or you are getting very funny shapes in the UMAP, you prefer probably to use PCA even if you are getting something that is less informative because you are not getting something with this kind of artifacts. Last one is deep elastic. Deep elastic is a method that is going to try to keep at the same time global features of your landscape and local features. And for that, there are many different parameters. Usually, you don't really need to change these parameters, but we are going to see what these different parameters do. And well, if you really need to change something because you want to get a slightly different representation or tune a little bit what you are seeing, you can modify them. They are all of them in the advanced section. First parameter is the number of clusters that will determine how well deep elastic will be able to approximate the overall shape of your high-dimensional space. We will see later on how to provide a good number of initial clusters or to have an idea of how many clusters you could expect from your landscape. Then we have this initial explosion power, final explosion power. So the idea of this deep elastic is that it's going to first take your initial clusters and it's going to kind of move them very far away with respect to each other. So it's going to learn first how to place the different clusters in space. And then it's going to go progressively trying to bring them closer and closer. And this final explosion power will determine how close it will be able to bring those clusters. Then we have parameters for directional autoencoder, which are going to try to enforce more continuity or not in your reduced landscape. And cosine mapping lambda, which is for the cos function. Usually you don't need to change that and you can put it to 1 and you will get good enough results. Once you have determined the method you want to use, you can click on execute and you will get a new set of particles. Let's compare the input and the output. Okay, so in the left we have the input. You can see these are the Cernic particles because we have here the vector of the Cernics, but nothing more. And if we compare to the particles of the reduce coming from the reduce protocol, we are seeing here that in the set red, we are getting a vector of 3 components because in this case I have used the 3D landscape option, which are the ones determining how to reduce this Cernic vector based on UMAP, PCA, or deep elastic into something that we can visualize that is more meaningful. And that's all. With this, you will get a set of particles that have not only the original landscape information, but also the reduced version of it. In next videos, we will see how we can use this original landscape and reduced version to do an interactive exploration of the landscape and get different conformations in real time. Thank you so much.